now that we have shown that the derivative and the antiderivative of power series converge with the same radius of convergence, we can apply that idea to geometric series to show that other functions can be represented as power series. In particular, I would like to look at the function f of x equals natural log of 1 plus x. Now, natural log of 1 plus x has a derivative of 1 over 1 plus x. So that means that we can write it as the antiderivative of 1 over 1 plus x dx. Another way to think about that is that's the antiderivative of 1 over 1 minus a negative x dx. And so natural log of 1 plus x can be thought of as the antiderivative of something that looks like the sum of a geometric series. So what we can do is we can write natural log of 1 plus x as the antiderivative of the sum from k equals 0 to infinity of negative x to the k power. It's the antiderivative of the sum of 1 minus x plus x squared minus x cubed plus x to the fourth minus x to the fifth plus etc. Another way to write negative x to the k power is to think about it as being negative 1 to the k, x to the k. So what we're going to do is we're going to anti-differentiate that series term by term. So I'm going to actually do it in the written out series first. I'm going to say the antiderivative of 1 is x, and then the antiderivative of x is x squared over 2. Antiderivative of x squared is x cubed over 3. The next term is x to the fourth over 4 plus x to the fifth over 5 minus x to the sixth over 6, etc. So I can look at the series and I can say, oh, well, this series is the sum from k equals 0 to infinity of negative 1 to the k over k plus 1 x to the k plus 1. And so natural log of 1 plus x can be thought of as the series negative 1 to the k over k plus 1, x to the k plus 1 power. If I'd like, I could re-index this. I could go from n equals 1 to infinity of negative 1 to the n minus 1 over n x to the n power. And that's generally how this is written, where n is, of course, k plus 1. So what I'm saying here is that natural log of 1 plus x can be rewritten as this infinite series, and I can say that it converges for the same radius of convergence as my geometric series. And so that's for x less than 1 in absolute value. Now it turns out that that gives us the radius of convergence, but in fact, we can say that it converges for negative 1 less than x less than or equal to 1. And that is because if I plug in x equals 1 here, then I get 1 to the n, and so that kind of cancels out. And I'm left with the sum of negative 1 to the n minus 1 over n. And that's an alternating series. And that alternating series, the terms go to 0, and so it converges. So I get the radius of convergence from the geometric series for 1 over 1 plus x. That radius of convergence is 1, but I still need to check the endpoints to see where that series converges. Now let's look at a plot of these in Desmos. Okay, so here I'm going to look at the function natural log of 1 plus x I'm going to get this to plot natural log of 1 plus x. Okay. And I'm going to plot with it my geometric sum. So I'm going to start, or my sum that came from the geometric series. So here is the tangent line. So that's just x. That's the first term, x. If I add the next term, that's going to be x minus x squared over 2. And then adding the next term is a plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5 minus x to the 6th over 6th plus x to the 7th over 7th. I keep adding terms, and I want you to notice that this series does converge to natural log of 1 plus x, but only converges to natural log of 1 plus x between minus 1 and 1. Nowhere else. If you look at x beyond 1, it does not converge to natural log of 1 plus x. And then if you look at x equals minus 1, well, for x equals minus 1, that's the natural log of 0. And the natural log of 0 does not exist. So at that discontinuity, this series cannot converge beyond, say, x equals negative 1. In fact, it doesn't converge at x equals negative 1. And so we see the same phenomena that we saw in the last video, whereas we have the function natural log of 1 plus x. It is a discontinuity at x equals negative 1. And so that actually really defines the radius of convergence of our series. Because of that discontinuity, it cannot converge past x equals negative 1. And so the radius of convergence ends up being 1. Okay, but we can actually use this information to actually find the sums of some interesting series. In particular, what is this series when x equals 1? So what we're saying is what is the natural log of 1 plus 1? Well, the natural log of 1 plus 1, that's when x equals 1. So that's going to look like kind of writing out the terms in the series. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth, etc. And you might recall this is the alternating harmonic series, which we showed converges in an earlier lesson. In fact, we showed that this series converged to about 0.693, but now we know that that decimal approximation is the decimal approximation of natural log of 2. So the alternating harmonic series converges to natural log of 2 because of the fact that I can rewrite natural log of 1 plus x using the antiderivative of a geometric series. So let's do one more function. That function is going to be the arctangent of x. You'll remember that the derivative of the arctangent of x is 1 over 1 plus x squared. So that means that the antiderivative of 1 over 1 plus x squared is the arctangent of x. We can think about this as being 1 over 1 minus a negative x squared. And that is a series that we found in the previous video. We saw that that series was the sum from k equals 0 to infinity of negative 1 to the k x to the 2k. In other words, arctangent of x is the antiderivative term by term of the series 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus x to the 10th, etc. And so just like we did with the natural log, we can integrate term by term to find the series for arctangent of x. So integral of 1 is x, antiderivative of x squared is x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, plus x to the 9th over 9, minus x to the 11th over 11, etc. So this series looks like the sum from k equals 0 to infinity. Integrating term by term, the negative 1 to the k stays there. The antiderivative of x to the 2k is 1 over 2k plus 1, x to the 2k plus 1. And so this is a series that represents arctangent of x. In fact, we know that this series converges for x between negative 1 and 1. That is simply because the geometric series that it came from converged between minus 1 and 1. We'd have to check negative 1 and 1 separately. So if we plug in x equals 1 in particular, notice that then we're looking at this sum of negative 1 to the k over 2k plus 1. And that's an alternating series in which the terms go to 0. So in fact, this does converge at x equals 1, but it does not converge if you plug in x equals minus 1. And so now we found a series that represents arctangent of x. So let's look again at Desmos. And let's plot arctangent of x. Arctangent of x, if we look at the first term in the series, there is x, and that gives us the tangent line. Okay, then the next term will be a minus x cubed over 3 that we add on. Then we add on an x to the 5th over 5, minus x to the 7th over 7, plus x to the 9 over 9. And so we just keep going and adding those terms. And notice that the series converges again between minus 1 and 1. It's interesting here because there's no discontinuity either at minus 1 or 1, but because this came from a geometric series initially, it's only going to converge between minus 1 and 1. So let's look at figuring out what the arctangent of 1 is using this series. So we're going to plug in x equals 1. That's going to give me 1 minus a third plus a fifth minus a seventh plus a ninth minus 11th, etc. And in fact, we've encountered this series before. We called that the Madhava series, also known as the Leibniz series. And so that series we had estimated before. We had gotten an estimate to 3 decimal places of 0.785. But now we know that that series actually equals the arctangent of 1. Okay, so if we want to find the arctangent of 1, we have to ask ourselves what angle has a tangent that's equal to 1. And if we want to know the angle where the tangent is 1, then that's the same thing as the angle where sine and cosine are equal. And so what angle are sine and cosine equal? That angle is pi over 4. So in fact, pi over 4 is the sum 1 minus a third plus a fifth minus a seventh, etc. And this actually gives you a way to estimate pi to a certain accuracy. So if you want to calculate digits of pi, you could take the sum, say, of 4 minus 4 thirds plus 4 fifths minus 4 sevenths plus 4 ninths minus 4 elevenths. You could take that sum, and that would give you an estimate of pi. The only problem with that is that it's a very slow converging series. That is not necessarily the fastest way to estimate pi. It converges to pi, but very, very slowly. But historically, people did use this series to try to calculate digits of pi.